Hello, this is Unit 7 Notes, Section 7.5, Proportions in Triangles. Starting off with a warm-up, how many similar triangles are in the figure? We noticed that if we were to draw a triangle and enlarge it, that this triangle is similar and proportional to the first triangle, and we can keep enlarging it, and we'll notice that we have a third one, and then we keep enlarging it, and we have a fourth one. So there are four similar triangles, and each, how are the lengths of the parallel segments related to each other? Well, each length is proportional by one additional side length. So we notice that if I were to take, let me get rid of this, if I were to take a side length here of the base, and I were to duplicate it, that there's actually two of them here, three of them here. I'll duplicate it again, and then duplicate one more time, and there's a fourth one. So in comparison to the top base, this would be 1/4 of it, 2/4, 3/4 of this final bottom base. All right. So we're going to learn about three things today: the side splitter theorem, the triangle midsegment theorem, and the triangle angle bisector theorem. We'll start with this one, the triangle midsegment theorem. What we have here is we have G as a midpoint, is halfway between D and E, and then we also have H as a midpoint. And that's outlined by, that is outlined by, I'm looking for this right here. There we go. It's outlined by it being halfway between E and F because of these tick marks. All right, so what we know is that GH is half of DF. We could also say that 2 GHs, two of the middle ones, GH, is equal to 1 of the DFs segments. And we also know that they're going to be parallel. So I'll put in some parallel marks, tick marks. And the triangle midsegment theorem, there's an extension to it called the side splitter theorem. And it simply says that AM, this segment right here, is in ratio with MB, as CN is in ratio with BN. Notice it doesn't involve our bases. So if I were to give it variables A, B, C, and D, it would be A over B is equivalent to C over D. You can think of I think of it like this, like a fraction bar. So B over A and D over C. Right? We could write as B over A and D over C. What we can't compare, again, are these bases right here. We can't compare this space to this space using side splitter. We have to approach that another method, which you'll see in a little bit. And then let's just note that these are not midpoints. These are not midpoints, but that it is still parallel. They can be midpoints, but in this case, these do not appear to be midpoints of BC and BA. The last thing we'll look at is the triangle angle bisector theorem. And so here we have UX, I'll call this A, I'll call this B, I'll call this C, and I'll call this D. So A over B is equivalent, that ratio is equivalent to the ratio of C over D. So if this angle is bisected, and here's the bisected angle, we see that the tick marks are congruent tick marks. If we see that, then we know we can use the triangle angle bisector theorem to set up our proportionalities. So now we're just going to do a few examples with that. Starting off with example 1, we have triangle JLN, and we have LN is 9.6. Let's put an L here. It got overlapped there. As you can see, the directions overlapped it, but that's supposed to be L. And so we are going to say that L is 9.6 units. And it wants us to solve for LM and MN. I'm going to put in random variables. I'll call LM X, and I'll call MN Y. Oops. And what we don't want to do is we don't want to use our side splitter theorem directly, because the side splitter theorem would say, write it 3/5 is equivalent to X over Y. The problem with using the side splitter theorem is that we would then have multivariable, and we can't come up with a solution for two variables. So what we're going to do instead is we're going to use the idea of similarity, but on a whole level. We'll call this whole thing 8. That way we can compare the smaller part, 3, to 8, the whole length of the triangle, and then this smaller part of the triangle, well, this upper triangle, X, to the whole length, 9.6. So again, we are doing part is to whole as part is to whole. 3 is to 8, 3 and 5 is 8, and X is to 9.6. We will then solve this using cross products. Oops. I'll solve this using cross products. 8X equals 28.8. Bring up my calculator here. Okay, so I have 9.6 times 3. I get 28.8. I'm going to divide that by 8, and we will get 3.6. 28.8 divided by 8 is 3.6. So I'll divide by 8, divide by 8, X is 3.6. So that means that LM is 3.6 as well. And the next one I'm going to solve for is MN, which is as simple as just saying 9.6, take away 3.6, which is 6. So I know that Y will be 6. And MN will be 6. But I'm going to prove it using proportions again, just so that we get the extra practice of proportions. So we'll say Y, in this case, Y is to 9.6. Oops. Y is to 9.6 as 5. That's the proportional part. See how they match here? 5 is to 8. And from here, we'll find cross products. So 8Y is 48, I believe. Let me just double check. We got 9.6 times 5 is 48. 48 divided by 8. Yep. So we'll get 8Y equals 48. So Y has to be equal to 6. So we just proved both of these by using proportions. So MN has to equal 6. Again, you could have just deducted it, but I'm just showing you that you can solve both of them and that they are proportional, and that's why they all work out. Okay. And then are the sides divided into proportional segments? And the answer to that is yes. Yes. The sides are divided into proportional segments. By the side splitter theorem. which states that if we have two parallel parts, which we do, we have Km is parallel to Jn in this triangle. That means that their sides will have to be proportional. All right. Now, in our next example, suppose BD bisects sides A and C. So we have that this is congruent to this, this is congruent to this. So CD is congruent to DE, and CB is congruent to BA. It says, do they have to be parallel? And yes, the answer is yes. Yes. By the, right here, by the triangle midsegment theorem. Yes. What we'll say, yes, AE is parallel to BD by the, whoops, by the triangle midsegment theorem. And I'll just put in some parallel tick marks here just to make that confirmation. All right, the next one, side splitter theorem. Here's an example where we can solve for side splitting, but we cannot solve in the same way for our bases. So Y is a base here, it's UV. ST is another base. So if I want to work with those, I need to compare it to the base I know, which is 30. So we just have to be careful here. We can only use side splitter for x's. So here's what I'll do. I'll grab these right here. I'll grab 4 and x plus 2 and 3 and x. So say 4 is in ratio with x plus 2, which is in proportion with the ratio of 3 and x. So I will find the cross products. We have 4x equals 3 times x plus 2. Make sure you use your distributive property. You don't need to write this middle step in, but just make sure you are multiplying 3 times x and 3 times 2. We solve for x is 6. Whoops, sorry, I'm just moving everything around. Whoa. Moving everything around. X is 6. So I will now, let me just get rid of that. We know that 6 plus 2 is 8 and 6. Makes sense. We have a 4 to 8 ratio and a 3 to 6 ratio. They are double. And so now when we go to solve for y and z, we have to use the information we know. So I'm going to use one of the sides. I'll use 12 and y. So say 12 is to y as this whole length is 24. So I'll say as 24 is to 30. So notice I'm creating a side angle side similarity. Side, angle, side. And I'm matching that with this side, this angle, and this side. So side angle side is how I'm comparing them. So 12 is to y. 12 is to y as 24 is to 30. We find our cross products and we will quickly solve for y. 24y equals 360. Whoa. All right, maybe I should just leave that up. All right. So we have, where am I? Right here. 24y, 30 times 12 is 360. So 360 divided by 24 is 15. And yep, so divided by 24, y is 15. Okay, actually, that should be right here. So we have x is 6, we have y is 15, and the last part is solving for z. We're going to use the same ratio. We'll say 24 is to 30, but instead we will say 16 is to z. So 16 is to z as 24 is to 30. And we solve z is 24z equals 16 times 30 is 480. Yep, 480 divided by 24. We get z is 20. All right, our explanation is there. We found our cross products and we solved them. So here we see a corollary or an extension to the side splitter theorem, and it says that you don't need just two triangles; you can have more than two, and that we don't even need a triangle at all. We can use this with parallel lines cut by transversals. So we have parallel lines L, M, N, and transversal AB or AC and DF. So you see here that if I extend these lines. And we look for the intersection, that we can tell it actually is just one big triangle cut into different portions. So AB is to BC as DE is to EF. So I'll label that R, S, T, and U. So it's the same as saying R is to S as T is to U. Again, just you can look at your parallel line as your fraction bar when you're doing this. So here's a real-world example. A reflecting pool is separated by walkways parallel to Lincoln Street, Jefferson Street, which are parallel to each other. The city wants to add additional tilling around the pool. So how much tilling does X feet represent, and how much tilling does Y feet represent? So here, if we kind of like turn our heads a little bit, we see that we have these parallel lines right here. Oh, let me pick a different color. That's a little bit better. So you have that parallel line and these two parallel lines. So, oops. And so these are kind of like our fraction bars. So we're going to compare x to 60, so x over 60. And then we go left to right, so we're going to go left to right again, 24 to 72. And we will find our cross products. So 72x equals 60 times 24 is 1440. And divide 1440 by 72, and we should get 20. Yep, good. So we divide it by 72. Oops. X is 20 feet. I mean, makes sense. 20, 40, 60, 24, 48, 72. So they are in proportion 1 to 3. And we're going to do the same thing, but we will now do 60 and 24. And 72 and Y. Find our cross products. So we get 60y is equal to 1,728. Divide both sides by 60, and we get y is equal to 28.8 feet. It's okay, it's a decimal. It's proportional. Everything doesn't have to be a whole number. So I'll just come back and label it, why not? We got 28.8 feet and we get 20 feet. So real world example using the side splitter theorem. Our last concept is the angle bisector theorem, triangle angle bisector theorem. So here it wants to know, are they similar? Well, the first thing I'm going to do is just see, are they in ratio with one another? So 7.5 is to 10, 10.5. So 7.5 is to 10.5 as 10 is to 14. We want to make sure we're jumping from triangle to triangle because that's what our theorem states, that we should be comparing this part, mn to kn, and then ml to kl. So if I find my cross products, I get 10.5 times 10 is 105. And let's just make sure that 7.5 times 14 is also 105, which it is. So we've demonstrated that we have proportional sides, but the problem is that we do not have proportional angle. Already starting this back up, we have, I think we left off right here where the angle is in the wrong position. So if we were demonstrating similarity, we would need the angle to be here, which goes against the theorem that we're working with for side angle side similarity. So what we can conclude is that these right here, that these two triangles, triangle LKN we'll say is not similar to triangle LMN because the position of the angle, the position of the congruent angle, are not included between the proportional sides. All right. We're going to skip this problem and we'll go on to our last example, example 5. So what are the values of AD? Here we have an unknown value x and 10. We have 16 and we do not know this side, but we can use the variables at hand to solve for that. So I'm going to leave it still in variable form. We'll do 13 minus x. If x were to be 3, then this would be 10. It would be 13 minus 3 is 10 because this whole side is 13. So I now can set up in a proportion. Here's one ratio. I'll say 13 minus x over x equals 16 over 10. So again, we're going from CD to DA or AD, and so we go from the left triangle to the right triangle. We then go back to the left triangle, back to the right triangle for proportions. So we have this proportion set up. We'll find our cross products. So 16x is equal to 10 times 13 minus x. 16x is equivalent to 130 minus 10x. We have 26x equals 130. We're going to divide both sides by 26. X is 5. So, if x is 5, we know that AD equals x, so AD equals 5. Lastly, we have CD equals 13 minus x. CD equals 13 minus 5. Oops. CD equals 8. Okay. One problem left. We'll set this up as 3x minus 7 over 12 equals 3x plus 3 over 18. Find our cross products. Don't forget to distribute across all terms. 18 times 3, 18 times -7. So we have 54x minus 126 equals 36x plus 36. We'll take 36x away from both sides. We have 18. Yep. And then 126. So 18x minus 126 equals 36. Add 126 to both sides. 18x equals 162. Yep, so x is 9. And now that x is 9, we can find GH and GK. We substitute in 9. So 27 and 3 is 30. And then GK is 3x minus 7. We substitute in our 9. 27 minus 7 is 20. So GK is 20 and GH is 30. And that's it. Good luck with your homework.